Does anybody have any questions before we get started? Last time we talked about a process flow, a CMOS process flow. Any semiconductor process has a flow that can be described somewhat like we did last time. And what's the reason for knowing the basics about a process flow for a given design? What's the reason you need to know what that process flow is? Yes?
It changes your calculation.
It changes your calculations?
Yeah, and it also affects like what you can connect and what you can't connect.
Yeah, that's the most important thing. It shows what you can do and what you can't do. So for example, on that process we looked at last time, did we put metal under poly 1?
No.
No. The reason we can't put it under poly 1, metal went on after poly 2. So when you look at that process flow, you'll know what you can put together and what you can't put together. And if you don't know that process flow, it's impossible to know what you can connect and what you can't connect. Does that make sense? Okay, so that's the reason I think we need to know the basics about a particular process flow. Oh, I've got something different on the slide here. Bipolar devices. We're gonna talk about bipolar transistors today. Are we making a step forward or a step backwards talking about bipolar devices? Backwards. Bipolar devices came out in the late 40s, and they were the dominant devices that were used to make ICs up until close to 1975 and 1980. And now MOS devices are kind of the dominant device we use. So we're taking a step backwards. No, not really. We're not really taking a step backwards. There's still a lot of bipolar processes being designed today. It's interesting, you go to industry, and there was a period of time in the mid-70s where industry was struggling with trying to retrain bipolar circuit designers to do MOS circuit design. Most of those people have retired. Now industry seems to have another problem. We seem to have a shortage of people that can do bipolar circuit design. So there's still bipolar circuit design being done, sometimes in bipolar processes. A lot of your linear ICs still are built in bipolar processes. And some of the more high performance processes have both bipolar and MOS device available. Okay. So we're not going to take a step back. We're talking about bipolar transistors. It's important we understand how they operate as well. We just don't have the luxury of having access to a bipolar process to work with in the laboratory or get fabrication done in a bipolar process. That could be done as well. We just don't have access to that. A review from last lecture, we went through a typical process flow for a bulk N-well CMOS process. And that process flow is very similar to the process flow for the process we've been working with in the laboratory in this course. And we saw how all the basic devices that we had to work with, the major devices we had to work with, could be formed in this process. We looked at a top view and a cross-sectional view, and then we asked the question, what can we make and what can't we make with that particular process? Today is BJTs. I'll try to talk about how they operate, and I'll try to start developing models for the devices. We should have our first models for the bipolar transistors before the end of the lecture. Let's talk a little bit about carriers and doped semiconductors. We can dope with N-type or P-type impurities. I'm going to follow the same convention I had for slides for the MOS devices. If I use a green color, I'm assuming we've got N-type doped silicon. If I use the yellow color, we'll assume we've got P-type doped silicon. By the way, the processing equipment that you use to make a bipolar process is about the same equipment that you use to make a CMOS process. A few different steps, but most of the same equipment can be used for both processes. So if you look at an N-doped region, we can put a voltage across that region, and we'll probably get a current to flow, and it probably looks like a resistor. If you look at the carriers that are in the N-type region, those carriers are dominant electrons, and there's a small number of holes that are present, and those are typically short-term carriers. Every once in a while, a hole will appear and it will recombine with electron. Major current flow is going to be electron current. There will be a little bit of hole current, but mostly electron current.
What do you mean by hole current?
What?
What do you mean by hole current?
Hole, H-O-L-E. We have electrons in holes. A hole is a vacancy in a valence band. An electron, if you have electron moving, it's an extra element in the valence band.
Okay.
So when we talk about hole current, we're looking at how holes propagate through the silicon. If we're talking about electron currents, we're looking about how electrons propagate through the silicon. Okay. On a p-doped semiconductor, the current carriers are dominantly holes. So we have what looks like holes that propagate through that structure. Actually, what happens is electrons move to hole, electrons move to hole, and so forth. So it looks like the hole is moving around in the p-type material. So if you have n-type material, the majority carries your electrons, and the few holes that are contributing to current are referred to as minority carriers. Likewise, if you have p-type material, the majority carriers are holes, and the minority carriers are electrons. If you look at a MOS transistor, this is a cross-section of an N-channel MOS transistor, and if the device is going to be having current flowing, we're going to have an inversion layer in here. That inversion layer will be an N-type inversion layer, and the conduction of current in that channel region is going to be then by majority carriers. It'll be electrons in an N-type region. If you have a p-channel MOSFET, we still create an inversion layer to get current to flow in both the saturation region and the triode region. And there's a channel. And if that's an electrically induced p-type region, the carriers are what? Holes. So it's majority carriers that are associated with current flow in the channel. So the carriers in electrically induced p-channel region are also holes, are also majority carriers. So regardless of whether you have an N-channel or a p-channel transistor, the carriers in the channel that pretty much govern how the device operates are based upon majority carriers. I don't know why we talk about that. That wasn't really an issue up to this point. Let's look at a bipolar transistor. A bipolar transistor is typically a stacked region of NPN material or PNP material. So on the left, I have an NPN stack, and on the right, I have a PNP stack. I intentionally have one side more heavily doped than the other side. We're going to connect electrodes to those three regions. I'm going to call the region that's more heavily doped the emitter. I'm going to call the region that's more lightly doped on the outside the collector, and the region in between will be the base. And that'll be true for both PNP and NPN devices. So here's the symbol of an NPN transistor and a symbol of a PNP transistor. If you dope these devices appropriately, and you have the right dimensions, we form a bipolar transistor. Just because we put PNP or NPN together doesn't necessarily mean we form a bipolar transistor or a decent bipolar transistor. But if you have the dimensions correct and the doping levels correct, then we'll form a bipolar transistor. If you look at the bipolar devices here, they also show symmetry as the MOS device did. The MOS device was completely symmetric from drain to source with the device we looked at. Well, this is almost symmetric because the emitter and the collector are both of the same type material and the base is of the opposite type material. But it's not electrically symmetric because we have a different doping level on what we call the emitter than what we have on what we call the collector. So the electrical properties we're going to see are not symmetric, and consequently the designation of the collector and emitter is significant in a bipolar device. In a MOS device, since the device is symmetric, it didn't make a difference what we called the source and drain. But for the bipolar transistor, we will agree that the more heavily doped region will be called the emitter. If you look at the MOS transistor, the MOS transistor really has 4 terminals: a drain, a gate, a source, and a bulk. In contrast, the bipolar transistor has 3 terminals. Okay. However, most of the properties of the MOSFET that we needed to discuss the operation of some of the basic circuits so far in this course, we were able to neglect the bulk terminal. We have to always connect it, but it didn't have a major role in the electrical properties we were interested in. Okay? So in some sense, the MOS transistor still performs about like a 3-terminal device. So let's look at how the device operates. I'm first going to forward bias the base emitter junction of an NPN transistor. So I'm going to consider an NPN transistor. I'm going to forward bias the base emitter junction, and I'm going to look initially at operation in what's called the forward active region. We're going to see there are several regions of operation in a bipolar transistor, as there were in the MOS transistor. So we're going to start now in what we call the forward active region. Under forward bias, I've left the collector open right now. Current will flow into the base and out the emitter. In fact, what have we formed? A diode. And this current flow will be governed by what? The diode equation. Okay? When I was a student, bipolar transistors were kind of expensive. And sometimes if you burned out the transistor and you destroyed the base collector junction, you would oftentimes save the transistor and use the base emitter junction as a diode. So current flow is governed by the diode equation. The carriers in the emitter are electrons, so they're majority carriers. The carriers in the base are what? Holes, so they are they majority or minority carriers? What?
Minority.
Remember, holes in a p-type region were still majority carriers. So the current flow in the emitter is by majority carriers. The current flow in the base is by majority carriers. It just happens in one place they're holes, in one place they're electrons. Oh, but something happens. If you've got current flowing through this junction, you've got hole current here, and you've got electron current on the other side. So something has to change when they go across that junction to become majority carriers again. If those holes went across that PN junction, then they would be minority carriers in that emitter region. So when electrons pass into the base, and actually the current flows in this direction, but you recall that the convention that was established was that the current flow is in the opposite direction of electron flow. So as electrons are moving this way, right? Electrons are moving this way. When the electrons pass into the base region, they become minority carriers. And they quickly recombine with the holes, and then the current flowing through the rest of the base region is by holes, which is majority carriers. Okay, does that make sense? Okay. And now let's add another biasing source to this. I'm going to put a positive voltage from the collector to the base. So what am I doing to the base collector junction? Am I forward biasing or reverse biasing it? I forward bias the base emitter junction. What about the base collector junction? It's reverse bias. It's reverse bias. If you have reverse bias a junction, you're trying to force current flow or inhibit current flow. What are we trying to do if we reverse bias that junction? Inhibit current flow. So we're trying to force current flow in the base emitter junction. We're trying to inhibit current flow in the base collector junction. If you have a positive voltage, you put an electron there. What forces are applied to that electron if you put a positive voltage in a region and have an electron there? That electron is attracted towards the positive side of the supply voltage, right? Okay. So let's see what happens. We've got electrons coming here, and then they get into this base region. And once they get in the base region, they say, aha, I've arrived in the base region, and I'm a minority carrier. And the bias for the base emitter is trying to make that minority carrier that appears here exit as base current, right? But while that electron is here, there's a reverse bias on the base collector junction. There's a positive voltage on the collector. And what we're doing is we're providing a force on that electron to go where? To the collector. So there's contention going on here. There's a battle going on. The question is, when that electron appears in that base region, is the base going to win and convert to whole current and have it exit through the base? Or is the bias on the collector going to win and attract it across the base collector junction, which is reverse bias, and contribute to collector current? Yes?
What is going to happen when you have a positive and negative voltage applied at the base?
We're not applying a positive and negative voltage to the base. You can think of this as ground if you want to for the purpose of this illustration. So I'm putting a negative voltage on the emitter and a positive voltage on the collector then. Good question, but I'm not providing two separate. If I connected these together, then we'd have a problem with Kirchhoff's voltage law around the loop, but I've not done that. Good question. So, if we look at this region here and expand it then, this electron appears in the base region. Of course, a lot of them will appear. And there's a force to have it recombine with a hole and exit to the left on this drawing as base current, right? But we said there was also a force applied by the voltage on the collector to have it come across this reverse bias junction and contribute to collector current. So, while the minority carriers are present in the base region, they can be attracted to the collector with this reverse bias base collector junction. And then they'll contribute to collector current. I wonder what we can do in a device. Do we want that to happen? Do we want the carriers that are in the minority carriers that appear in the base region, do we want them to exit through the base? Or do we want them to exit through the collector? Collector. Yeah, we would like them to exit through the collector. We're going to see in a minute that if we can have most of them exiting through the collector, a small amount of power into the base may control a large current flow from the emitter to the collector. Okay. So what will happen is a win-win situation. The base gets some, and the collector gets some. Okay. The size and the thickness of the base region and the relative doping levels play a key role in the percent of the minority carriers that get into the base region that will actually become collector current. Conceptually, we can probably get some idea about what we would want to do to make this structure to have a high percentage of the minority carriers become collector current. If you make that base region real thick, then they'd have a lot of time to recombine with holes and exit as base current. If you make that base region very thin, then they don't have to travel very far to become collector current. Make sense? So the thickness and the doping levels of the base region, and of course the corresponding collector and emitter regions, will determine what percent of the minority carriers contribute to collector current. The efficiency at which minority carriers injected into the base contribute to collector current is termed alpha. So alpha could be anywhere between 0 and 1. If alpha is 0, it means that none of them make it to the collector. If alpha were equal to 1, it means they'd all make it to the collector. Alpha is always less than 1, of course, but for what we consider to be a good bipolar transistor, which we'll see why that's important later, alpha is very close to 1. For a good transistor, alpha is typically between 0.99 and 0.999. Between 99% and 99.9% of the minority carriers become contributors to the collector current. Making the base region very thin makes the alpha large. If you make it too thin, you'll lose the region and the device will quit working. Okay? Principal operation of PNPs are the same. You forward bias the base emitter junction. You inject, in this case, holes into the base region, and you reverse bias the base collector junction, and those holes are now again attracted to the collector. If you look at the performance of an NPN and a PNP transistor, everything else being the same, the performance of the NPN transistor is usually modestly better than that of the PNP transistor, primarily because the mobility of the electrons is higher than the mobility of the holes. Similar thing we observed for MOS devices. So, why do we talk about majority and minority carriers? Well, it's probably necessary to talk about those carriers to describe how a bipolar transistor operates. But we can just make an observation. In contrast to MOS device, where current flow in the channel, that's what we're interested in what's going on, is by majority carriers. In a bipolar transistor, current flow in the critical base region is by minority carriers. The current flow that affects the operation of the device. Yes?
You said you forward bias the base emitter. What was it? With the PNP. Are you still trying to get the current flow from emitter to collector?
Yes, that's correct. We still try to get the current flow from emitter to collector. And so we do that by forcing a current into the base region or into the emitter region by forward biasing the base emitter junction. Okay. If you look at the current in a three-terminal device, we know that the sum of the three currents has to be zero by Kirchhoff's current law. So we kind of observe the collector current plus the base current is equal to negative the emitter current. So when we're modeling the device, we have a choice of getting models for any two of those variables. We can model the emitter current and the collector current. We can model the emitter current and the base current, or we can model the collector current and the base current. And then we get the other current by Kirchhoff's current law. So the collector current plus the base current is equal to the negative of the emitter current, where I'm using the convention that the current is defined to be the current flowing into that corresponding node. By definition, the efficiency of emitter current becoming collector current was alpha. So I can say the collector current is equal to minus alpha IE. And the minus sign is there because we talked about the current flowing out of the collector rather than into the collector. So the collector current is equal to minus alpha E. If alpha is very close to 1, the collector current and the emitter current are very nearly the same in magnitude. They're just opposite in sign. Make sense? From these two equations, I can obtain a relationship between the collector current and the base current by just eliminating the emitter current between these two equations. So I can observe that the collector current is equal to alpha over 1 minus alpha times the base current. Okay, yes?
So from base to emitter is like a forward bias diode. From base to collector is like a reverse bias diode.
Yep.
Then emitter to collector is like a resistor.
No, don't. It's a nonlinear device, so don't try to think of that as being a resistor.
Okay.
A good question, but it's a nonlinear device. We'll get the relationship shortly.
Okay.
We defined the parameter beta to be alpha over 1 minus alpha. So if you want to characterize the efficiency of collector current, of emitter current contributing to collector current, we could either use alpha or we could use beta. And it's another measure of the efficiency. So beta is equal to alpha over 1 minus alpha. If alpha is close to 1, this is small, so beta is pretty large for a good transistor. So we can say the collector current then is equal to beta times the base current. So what am I thinking of here? I'm modeling a device. I can look at models for any two of those three currents. I'm thinking now of modeling the collector current and the base current. Okay. Beta is typically, you go ahead and put typical values of alpha in that we talked about before. Beta is typically between 50 and 1,000. So beta is very large for a good transistor. So we can think of a bipolar transistor as, so if the input is the base current and the output is a collector current, we can think of the bipolar transistor as a current amplifier. It amplifies the base current by beta. And if beta is large, this current amplifier has a large gain. I wonder why Shockley and Brad Dean and Barton were really excited when they came up with this bipolar transistor. What did they have? What? They had vacuum tubes to work with before, right? What did they come up with now? An active device that was cold that acts like a what? Current amplifier with a great big gain. Make sense? Wow, that was a neat device they had. So it can be thought of as a current amplifier with a large current gain. If you think of a MOS transistor operating in the saturation region, what can it be thought of as? With an expression. So this represents the relationship between the port variables at the base and the collector. If you look at the MOS transistor, we have in the saturation region, we have the drain current is equal to mu Cox W over 2L times VGS minus VTH squared. So the controlling variable is the gate to source voltage, and it controls the current. So the MOS transistor is inherently a transconductance amplifier because the output current is controlled by the input voltage. The bipolar transistor is inherently a current amplifier. Now we trick these devices all the time into having different port variables than they inherently are designed to work with. We will trick by clever circuit techniques a MOS transistor to serve as the voltage amplifier. And we'll trick a bipolar transistor to serving as a voltage amplifier as well. The devices are inherently, though, a transconductance amplifier and a current amplifier respectively. Make sense? Devices are transconductance and current amplifiers, but we will make them operate in different ways depending on what circuit we put them in. Let's try to model this device. We know the current flow in the base. Current flow in the base, we said, was governed by the diode equation. So the base current is equal to, what's the diode equation? IS tilde? Well, we call it IS, and when we talk about a diode, I put tilde in here for a reason will become apparent in a minute. Some constant IS, tilde, times e to the VV over VT. That's the diode equation, right? So we see that the collector current varies exponentially with the base emitter voltage. So if you want to think of it as a transconductance type device, in the MOS case, the current varied with the square of the gate to source voltage in the saturation region. In the bipolar device, the current varies with the exponentiation of the base emitter voltage. Okay. Since the collector current is approximately beta times the base current, in fact, it's beta times base current in our model, it's beta times IS tilde e to the VV over VT. I should have made that statement here. We see that the collector current varies exponentially with the base emitter voltage. I've got a model for the device. It's given here. How do we model the MOS transistor? We had expressions for the gate current and the drain current, right? One of them happened to be 0. Here I've got expressions for the collector current and the base current. So I've got a model. So here's our two models in the saturation region for the MOS device and the forward active region for the bipolar device, the exponential equation and the square law equation. So if you look at the gain, and if you look at the gain as the relationship between the current and the corresponding controlling port voltage, the voltage either from gate to source or from base to emitter, the gain is much higher for a bipolar device because there's an exponential relationship rather than a square law relationship between the controlling variables. This high gain property this device has is very useful in many applications. And that's probably the major reason that a lot of your linear ICs are still built with the bipolar processes. So the convention we're going to follow is pick IC and IB as the dependent variables and VBE and VCE. VCE hasn't appeared in anything yet as the independent variables. It's exactly what we did for the MOSFET. We treated the port voltages, VDS and VGS, as the independent variables, and the port currents, the drain current and the gate current, as the dependent variables. Okay? So here's a summary of the model we have. The base current, the collector current, and of course that VT we had from the diode equation was K times T, which is temperature in Kelvin divided by the charge of an electron. It's only a problem. There's a problem with this though. This has the properties we're looking for. It has the right relationship between the port variables, except the notation I use is not standard. So if you go to industry and use this as your model, they'll say, what's IS tilde? I've never seen IS tilde before. Okay. If you look at this equation, beta appears here in the collector current expression. I could put beta in this expression and have a different coefficient and still have the same equations. I have a choice of where I put beta. I won't change the model. I just have a different way I can define parameters for that model. So it can be shown that IS tilde, first of all, is proportional to the area of the emitter. If you double the base emitter area, you should double the current. Yes?
Does this stay the same for NPN and PNP? Are the equations the same?
The equations are the same. Current's in opposite directions, so let's not worry about the sign. Very much like the MOS device. Parameters may be different in front here, but the equations are the same. So I'm going to define the parameter JS by this expression. I'm going to say JS is equal to IS tilde times beta over AE. Or equivalently, I'm going to assume that IS tilde is equal to 1 over beta times JS AE. So I'm defining a new parameter JS. JS is related to IS tilde, and it's related to beta by this expression. If I do that, I can go back to this equation and replace IS tilde by beta to the minus 1 JS AE. Right? So just define a new parameter. Oh, by the way, this parameter, people will know what you're talking about. So if I make that substitution, I can express the base current and the collector current this way. Now what have I done? I've moved the beta in this expression, in these expressions, from the collector current equation to the base current equation. What's the reason for doing that? It allows us to be compatible with the models other people have developed. I can call this quantity here IS if I want to. And a lot of people do that. So the product of JS and the emitter area, we can call it IS. So this would be IC is equal to IS e to the V over VT. That's the value equation then, right? Use the value equation for the collector current rather than for the base current. And then this becomes IS over beta e to the VT over VT. So JS is termed the saturation current density. There's two process parameters that we have now, JS and beta. For the MOS process, what do we have for process parameters? What were process parameters here? Mu, Cox, and VTH, right? So we have three process parameters for the MOS process. We have two process parameters here. This has one geometric parameter, W over L. The bipolar transistor has one geometric parameter. What's it? AE, area of the emitter. Not the area of the base, not the area of the collector. The area of the emitter. We're going to see the emitter areas don't have to be the same as the base and the collector areas. We're on a cross section we look at. When we make the device, they don't have to be the same.
So that's constant with both N and P.
Pardon?
And that's constant with both N and P types. Like, they're both based on the emitter?
Yep, they're both based on the emitter area. Same expression applies for both types. The parameter JS will be different. And then there's two physical constants, K and Q, and an environmental parameter T. At room temperature, we saw before the thermal voltage is about 25 millivolts. GS is very small. It's around 0.25 femtoamps per square micron. Okay. Wow. Is it so small we can neglect it? So if the area is 1 square micron, this would be of the order of magnitude of a femtoamp. Can we neglect it? Well, no, because VB or VT, VBE might be around 0.6 volts. 0.6 volts by 25 millivolts, you exponentiate a very big, a big exponent. So that gets very big. So you get large currents flowing here. You do that because the coefficient is small, but that exponentiated term is very large. Here's a plot of the collector current versus the base emitter voltage for JS of 0.25 femtoamps per square micron and an emitter area of 400 square microns. And we observe that as VDE goes from about 0.55 to about 0.58, the collector current varies by 2 orders of magnitude. Due to the fact that there's an exponential relationship between the collector current and the base emitter voltage. That doesn't look like exponential. Why does it look like exponential? My scale, I just zoomed into a small region. So that relationship really is exponential, but I'm just looking at a small segment of it. So I just want to point out that the base emitter voltage is close to 0.6 volts for a two-decade change in collector current. Actually, if you go back and look at over a slide, the bigger range, from about little less than 0.5 to about little more than 0.7, over a 1, 2, 3, 4, almost 5-decade range, the base emitter voltage doesn't change very much from 0.6 volts. So we get a great big change in current for a very small change in base emitter voltage around 0.6 volts. If I plot the output characteristics of the device, I can look at the collector current as a function of the collector emitter voltage, but notice the collector current doesn't depend on the collector emitter voltage, so these would be straight lines. And I can plot them for either different values of VBE or different values of IB. For the MOS device, when we looked at the output characteristics, we looked at different values of VGS. If I plot them for different values of VBE, I have like VBE of 0.55, 0.551, 0.552. Small change in VBE would result in a nonlinear space in these curves. It's more commonly that we express these in terms of base current values. Since the collector current is proportional to the base current, then they would be uniformly spaced. So this might be for base current of 10 microamps, 20 microamps, 30 microamps, 40 microamps, 50 microamps, 60 microamps. The current would go up almost linearly with those increments than if we have these for different values of base current. Here's a better model of the output characteristics. Now, the model we have so far that we described was in the forward active region. It only described this region out here, but you take a real device, you'll see it tails off if you get the collector emitter voltage small. If you don't have a good force on those electrons, they don't become collector current anymore. What's this starting to look like? What's this starting to look like? Oh, it looks like a MOSFET. Devil's in the detail of what the spacings are of those curves, but it's starting to look more like a MOSFET, isn't it? Or at least a three-terminal device that have characteristics somewhat similar to those of MOSFET. We can plot a transition between where the curves are flat and where they start to come down. If we're to the right of that, we're in what we call the forward active region. That's how I describe the operation of the device. If we're to the left of that curve, we're in saturation. And if the current is essentially zero, we're in cutoff. So we've defined three regions of operation, much like we did for the MOSFET. MOSFET had what three regions? Saturation, cutoff, triode. Bipolar transistor has forward active, saturation, and cutoff. That's the good news. How many words in the English language? A lot. There's so many words in the English language, you probably don't really have to reuse words very often. We've used the word saturation twice. Once to describe a region of operation for the MOS device, once to describe a region of operation for the bipolar device. For the MOS device, the saturation region corresponded to this right here. For the bipolar device, the term saturation corresponds to this region back here. I think it's somewhat unfortunate that we happen to use the same term to refer to entirely different regions of operation. Does that make sense? I can't defend it. It's the way it's done.
So why did they call that side saturation? I thought saturation is just like heading towards convergence.
Well, why is saturation, I guess, on the left side, out in like the triode region on the MOSFET? Why is it over there? So like,
English language only has so many words, right? We have to reuse a word. We can go back in and maybe comment about how the devices are operating and see why the term was used. But I think as far as we're concerned, we just need to remember that one's called saturation that means entirely different region for the MOS device than the bipolar device. So saturation in the bipolar device is analogous to triode in the MOS device. Saturation in the MOS device is analogous to forward active in the bipolar device. Cutoff and cutoff mean the same thing. That's all for the big things. Thank you.
So then if they model it slowly, could you also use a MOS transistor as a current amplifier?
No, because
you would need the BJT for it to
we could trick a MOS transistor to act like a current amplifier as well. We'll talk about circuits that do that later, but there's no current that flows into the gate. So you can't amplify a current that doesn't flow.
Okay.
Or you could think or you could think of a MOS transistor having an infinite current gate if you wanted to.
Okay. All right. Then I'll leave your question.
Okay.
Thank you.
A question, I guess, if we had time.